Okay, so I want to take a quick video to walk through a simply supported beam question where there's a uniformly distributed load and how we'd solve it. So in this beam, we have two supports, left and right, keeping it in equilibrium. We have 2 point loads acting down on it, 10 and 5, and we have a UDL, uniformly distributed load of 10 kilonewtons per meter acting across the entire length of the beam. And so I've come up with some keynotes to help people remember how to resolve these things. So when we want to resolve a UDL, we want to create we want to show it acting on the beam as a point load. How do we do that? You multiply the length of the beam that the UDL is acting across by the units given to you. So in this, we were told the UDL had a value of 10 kilonewtons per meter. So for every meter this acted on, there was 10 kilonewtons of force. So we multiply our 10 kilonewtons per meter by our 13 meters, and it tells us we have a force of 130 kilonewtons acting somewhere on this beam. Where does it act? Well, remember what UDL's, uniform distributed loads, again, that they act at the center. So at this example, it acts across the entire length of the beam, which makes our life a bit easier because it acts the same value left and right. And if it acts at the center of 13 over 2 is 6.5 meters. So now we know we can replace that UDL with a point load, and the point load is 130 kilonewtons, and it acts 6.5 meters away from the beam. I'd advise everybody to redraw a beam when you look at a sample like this, and the key thing to remember, the position of P1 and P2 doesn't change in this question. So even though we're putting in our UDL as a point load, P1 and P2 should stay exactly where they are. So P1 should still be 10 meters from L, and P2 should still be 12 meters. I've rubbed that out by accident there, but it should still be 12 meters away from L. So if I want to redraw it, what I would do first of all is I'd remove the lengths that are in there, and I would keep P1 and P2 in, vaguely looking like where they should have been. So I know I've got a force somewhere of 130 kilonewtons. I can draw that acting in, and I know it acts 6.5 meters in the center of the beam. In this case, because it acts over the entire length of the beam, I know it's going to act 6.5 meters from L and also from R. So R should also equal 6.5. So I want to draw this in 6.5 meters. And this is the bit where most people fall down. So 10 kilonewtons, or P1, we know it acts 10 meters away from L. I need to update this. So to continue acting at 10 meters, I add in 3.5. And now I know that distance. So from here to here is 10 meters. I'm going to rub this line below out. And if I go the opposite direction, think about it, I know P2, so again P1, P2, I know P2 acts 12 meters away from L, and to do that, this value must be 2, and I know the entire length of my beam should be 13 meters, so this value should be 1. And now I should be ready to solve this question. Okay, the next thing I want to do is I want to get a statement of my forces. So first of all, to be in equilibrium, this beam can't be moving anywhere, and it can't be rotating or twisting in any way. So to not be moving in any direction, the forces up have to equal my forces coming down, and for no twisting or rotating, any of my moments clockwise have to equal my moments counterclockwise. So if I look at forces up equal forces down, going up, the forces I can see that are acting up, these arrows upwards are left and right, downwards are the 3 on top, and that lets me ultimately get to this statement of forces that left plus right equals 145 kilonewtons. Okay, so I can use both of these statements for equilibrium to go and solve this question. I've used the forces going up equal to forces down to get that initial statement. Now I'm going to use moments clockwise equal moments counterclockwise. Ultimately, I could rearrange this and say the moments clockwise minus the moments counterclockwise should equal to 0. And that's what I'm going to do. So if I take the moments about point L to equal 0, I can solve to find a value for R. So I can fill in that statement that the sum of the moments about L equals 0. And I remember that moments are force by perpendicular distance. So at L, I've got 3 point loads on top. Then point loads, if I was fixed here at L, they would want to point or to push clockwise. And so that all of these points want to push me this way. And I need to remember that that a moment is a force by a perpendicular distance. The second place students will fall down is this perpendicular distance. This is the entire distance from L to that point. So if I look at this, moments L, so looking at that moments about L, the 130 kilonewtons is 6.5 meters away from L. So 130 by 6.5 plus the 10 is 10 meters away from L, and you can always remember it if you say how far away is it from the moment I'm taking, or from the point I'm taking the moments about. So the 10 kilonewtons by what's my perpendicular distance? It's 10. So it's the total distance away from L. It's not just that 3.5. It's the entire distance away from L. So moment is force by perpendicular distance. It's 10 meters away. And that will catch students out. And my 5 kilonewtons, how far away is it? You should be shouting 12. So 5 by 12, it's 12 meters away. And the final force on this R wants to push me counterclockwise. So it's going to be a minus. So minus R times how far away is R from L? It's 13. So to be in equilibrium, all of these moments have to equal 0. And you go and you simplify that. So I've plugged this part into my calculator. It tells me it's equal to 1005. I bring my 13R over the other side of the bracket, of the equal sign, it becomes positive. So 1005 is equal to 13R. R is equal to 1005 divided by 13. So R is going to work out to be 77.3 kilonewtons. Now that I have a value for R, I know one of my forces. I need to go and find L, and I do this by taking that initial statement of forces and substituting the value in. So I said L plus R was equal to 145. So L plus 77.3 equals 145. L equals 145 minus 77.3. L equals go to the calculator, L equals 67.7 kilonewtons. Now I've got a value for left and right, L and R. I know the two forces that would keep this beam in equilibrium, and I've solved that question. And so the key thing to remember, if I can get this to work for me, walking through it, you resolve that UDL as a point load. So you replace that squiggly line with one of these. You get a statement of forces. Forces up equal forces down. And your moments should equal 0 too. When you're calculating your moment, remember to use the entire distance from the point you're taking the moments around. So in this case it's L. So our distance for the 130 is 6.5. Our distance for P1 is 10. Our distance for P2 is 12. and the distance from L to R is 13. They're the values I use. I can solve for right. I find the value, I go back to my statement of forces, and I find the value for L. That's how I finish off that question.